So, hmm, should probably increase the character limit. Let's do this much is coming to like 140 and make it like 200. Yes. Okay, let's see. There's the setting for this. Session. Let's do 200. See that 200 character limit. And let's change it here as well. 200. We'll change the rules. Let's stream info. Rules. Moderation. Settings. We under your somewhere. Yeah, short rules. 200 character. Yeah, saved. Nice. Yeah, so today we'll be back continuing the series. I hope to at least get through 2 of them today. I know they're a bit longer, but we'll see how it goes. And yeah, let me just double check that the stream is all working. Okay, it's updated correctly on Twitch and YouTube. Let's see. Okay, it's updated correctly on YouTube as well. Okay, cool. Let's get started.
Directly into our vertex shader. However, this is clearly not a feasible solution for drawing anything remotely
Also, hope you like the new chat boxes and stuff.
complicated. 3D models for modern games typically have thousands of triangles, if not more. So in this tutorial, we will cover how vertex buffers store data and can be bound to graphics pipelines. A vertex buffer is really just a chunk of memory that we pass into our vertex shader. We can put whatever data we would like into this memory as long as we tell our graphics pipeline how it is structured. The first way we structure this data is by grouping it into attributes. A vertex attribute is that is specified on a per vertex basis. So, for example, we could create a vertex attribute for our two-dimensional position. If this was our only vertex attribute, then our vertex buffer would look like this, where every two numbers are grouped together to make up the x and y position of our vec2 input variable. Now, let's say we want to specify an RGB color for each vertex. We could add a second vertex attribute, this time a vec3. If we add this to our vertex buffer, then our buffer would look like this. The first two values in the buffer are grouped together to make up the position attribute for the first vertex. The next three values are the red, green, and blue values. These will be grouped together to form the colors attribute. The next 5 values are used for the second vertex and so on. The other way this data can be structured is by grouping attributes into separate bindings. For example, if we add a third attribute, we could interleave all 3 attributes into a single binding, or have one binding per attribute. Really, any combination we would like. For each binding, we need to provide a vertex binding description at pipeline creation. In the description, we need to specify the binding index.
By the way, yesterday I did try getting the like CMake with the shielders to build, but I wasn't able to get it working. If anyone's able to find something about it, do let me know.
and the stride.
You're
We can
forgetting the
mostly ignore input
candles
rate.
here.
For now, this will always be input rate vertex, with the alternative being input rate instance for when working with instanced data. The stride specifies the interval in bytes from one entry to the next. So you can imagine a pointer at the start of a vertex buffer. The stride indicates how many bytes it needs to advance each time to get to the start of the next vertice's data. For each attribute, we must provide a vertex attribute description. Attribute descriptions need 4 pieces of information: the binding index for the vertex buffer the attribute is located in, the location value for the input in the vertex shader, the offset of the attribute in bytes from the vertex start, and a VK format value describing the type of data. For example, our color attribute could be in our first buffer at binding index 0. And the location we specified in the vertex shader is location 1. The offset would be 8 because the position has 4 bytes for the x component plus another 4 bytes for the y component. Therefore, the color attribute values start at an offset of 8 bytes from the start of the vertex data. And finally, the format specifies the data type of the attribute. So the color attribute is a vec3, which corresponds to VK format, R32, G32, B32, SFloat. These are some commonly used data types and formats. Note that even though the format implies a color-like structure,
Yeah, this is red, red, green, red, RGB, RGB.
we use the same format even if we are representing non-color data. For example, the vec2 position attribute would still use a VK format R32, G32, SFloat, even though it's not a color, the amount of memory allocations. So often, for something like vertex data, even if we have multiple bindings, we will only allocate one large vertex buffer and have each binding map to a different region of the same buffer. So is it better to use a single interleaved binding or one binding per attribute or something in between? I won't delve into this topic too much right now, as performance differences tend to be modest anyway, and there is no one right answer. Typically, a single interleaved binding would be the recommended way to go. And for simpler pipelines and basic algorithms, this is usually true. However, depending on your overall rendering pipeline, the algorithms being used, and even your specific hardware, using separate buffers may yield better performance. So for now, don't worry about it. Just keep this in the back of your mind. Data may be beneficial. Okay, let's get to coding. The first thing we're going to do is create a new header file for our model class. So I'm going to call my file lve_model.hpp.
New header file. It's taking time to load this header file. LVE model. And add something new. No. Okay, cool. Select. Did I save the changes? I did not. Save. Are there any changes there? Okay, they just deleted some lines. Version files, finish tutorial. Probably didn't need to put that one in, but there's commits. This is not push all up to here. Make sure everything is saved. Yeah, that's all saved. Now let's that's the model file. The 6 for whenever we change over here. Don't need any of that.
Create a header guard, and then add the LV
Sharp background. Namespace over here. Plus over here. Model. Private over here. Device. Let's see. Let's do hash include over device HTTP. On the side over device. VK buffer. VK buffer. Vortex buffer. And VK device. Memory. Vortex buffer memory. So, keep forgetting that it doesn't switch unless I click on this.
4 lines, paste them in, and moving on,
Okay.
for the public portion of the model class, I'm going to go to my first app header and just copy these 4
Event. Yes.
I'm going to go
Event vortex. And 32 here. Vortex dot. Make a public.
app header and just copy these 4 lines, paste them in,
Stores everything else. Hello.
and replace the class name with LVE model. We must delete the copy constructors because the model class manages the Vulkan
Also, only model. Replace it.
and memory objects. Now take notice that for buffer objects in Vulkan, the buffer and its assigned memory are 2 separate objects. Rather than memory being automatically assigned for the buffer, this puts us, the programmer, in control of memory management. Now add a public function, void bind, that takes a vk command buffer as the argument, then duplicate this line and rename the second function to draw.
Right.
Now jump
in. Void bind. VK command buffer. Buffer. So VK command buffer, bound buffer.
Now, jumping over to the vertex shader, first completely remove the hard-coded positions variable. We're going
A simple shadow board.
with layout bracket location equals 0, closing bracket in vec2 position. So here we've specified our first
Layout location equals 0 and vec2 position.
vertex attribute. Like before,
Let's see what plugin is there. Okay, let's enable. That's already enabled. This one, let's move. Let's. I'll have to restart.
the data type is still a vec2, but note that now we have this in keyword that signifies that this variable takes its value from a vertex buffer. The layout location sets the storage of where this variable value will come from. This is how we connect the attribute description to the variable we mean to reference in the shader.
Let's change setting.
And now replace positions at GL vertex index with just position. We don't need to use GL vertex index anymore because the position attribute
CLI not it. That is. Never. Make the charts permanent. Okay, let's just refresh. Okay, this one we close now. And
with the values from the vertex buffer. So remember that the vertex shader runs once for each vertex we provide. And each time, this position variable will contain a different x and y component from the vertex buffer. And that's it for the vertex shader. Back. Remember that the vertex shader
position. Yeah.
Each vertex we provide, and each time, this position variable will contain a different x and y component from the vertex buffer. And that's it for the vertex shader. Back in the model header, we are going to create a representation of our vertex attributes that's easy to work with.
Okay, let's just compile it for now. show in Explorer. Open in Explorer. No. And it has run. Okay.
Include the vector library GLM. You should have already downloaded this and connected it to your project way
Yeah.
tutorial 1, when we also
Okay, hash include glm glm.http.
for windowing. Just above the include for GLM, add the line define GLM force radians. This makes sure that no matter what system you're on,
Hash define glm force radians.
expect angles to be specified in radians, not degrees. Back in university, in a computer graphics course, I must have wasted 2 hours debugging an assignment because I was thinking in degrees when I should have been working in radians. Don't make the same mistake. Additionally, add a define GLM force depth 0 to 1. This will affect some
Okay.
GLM functions we will eventually use. This tells GLM to expect our depth buffer values to range from 0 to 1, opposed to negative 1 to 1, which is, if I'm remembering correctly, what OpenGL uses. So now,
Let me just add audio from this into the global audio. Global audio. Audio application. Add new. Yeah. Okay. What was it? Go to what was it called? App audio. Yeah. Let's rename this. Rename bracket app audio edge. Let's see. Let's go back to edge. Properties capture audio files. Yeah, nice. I'll just see if it's playing. Okay, it is not working. Strange. Let me put properties, audio properties. Monitor and output. Yeah, it's definitely not detecting it correctly. Audio. See. Actually, clear. Yeah, it's still not working. Let's just go back to what was working. Or move edge. Property is capture audio.
description type. Oh, add a private function, void create vertex buffers, that takes a const standard vector reference of type vertex vertices
This
argument.
is Vulkan.
Now, finally, for our header, update the model class constructor to take a LVE device reference device underneath the public annotation in the model class. Additionally, add a 1-to-1, which is, if I'm remembering correctly, what OpenGL uses. So now, just underneath the public annotation in the model class, create a struct vertex. So for now, all we have is a GLM vec2 position.
Struct vertex. GLM position and static std vector vk vertex input binding description. Yep, binding description.
Copy this line and paste.
Should include a vector.
But this time it will be get attribute descriptions and instead return vk vertex input attribute description type. Oh, and these should be descriptions with an S. Then add a private function, void create vertex buffers.
Void create vertex buffers. Let's see.
Standard vector reference of type vertex, vertices argument. Now, finally, for our header, update.
Yeah, that's const std vector vertex and vertices.
Constructor to take a LVE device reference device and const standard vector vertices reference as argument.
LVE device and device.
Okay.
This.
Now let's add our implementation. Create a new file, lve_model.cpp, and then include.
Can I just create from your new C++ class? Access LV model. And so let's just make one new C++. Only model and function load only model HP.
And add your namespace. Copy your constructor signature and the and paste them in.
Yeah, let's see, namespace only let's see what all it is.
Class name scope, and then initialize the device member variable. LVE device curly brace device. For the constructor
let's see, only model here for only device. Only model inverse file. Save.
vertex buffers and pass through the vertices argument. Next, add the class name scope to the destructor. And for the destructor body, we have vk destroy buffer, lve device.device, vertex buffer, and null pointer for our allocation callback. Then
create vertex buffers, vertices. We can destroy buffer, only device, not device, comma vertex buffer, comma null pointer.
lve device.device, vertex buffer memory, and null pointer. Okay, let's
Okay, free memory, away device, vertex buffer memory, and null pointer.
quickly talk about these allocation callbacks that we've routinely passed null pointers to. So we've seen that Vulkan lets us manage our buffers and memory separately. And the main reason for this is that allocating memory takes time, and there's a hard limit to the total number of active allocations that varies by GPU, typically only in the thousands though. So if we continue on as we have been, as soon as you want to create a scene of high complexity with many different types of models, this model class will quickly run into those max allocation limits. So the recommended solution is to allocate bigger chunks of memory and assign parts of them to particular resources. So just for the short term, to demonstrate and learn the basics of memory allocation, we will continue to do so manually. But I think eventually we will integrate a well-established allocator library like VMA. If you would like to read about what might go into creating a memory allocator yourself, I provided a link to a blog post by Kyle Halliday where he does just that. Now moving on, let's implement the create vertex buffers function. Grab the function signature, add your class name scope, and then in the function body, the first thing we'll do is set
void only model create vertex buffers, vertices.
vertex count member variable to static.
1 second. Oh, it seems to be raining outside right now. This is the first bit of solid rain that we have gotten in like 2 years, I think. Because last year didn't rain properly at all. And before that was the flooding. So a bunch of places got flooded here. And yeah, ever since then it hasn't rained properly. And now it's like it's raining. It's enough to call it rain. It's not comparable to what you get in India or whatever. But yeah, it's nice to have some rain over here. It will dirty all the cars, but it is worth it. Yeah, let's see. Vertex count, static cost. I don't even know the script. Let's see.
uint32 type vertices.size. Now,
first line script.
let's add an assertion that the vertex count is at least 3 so that we know our model class consists of at least 1.
Include CSR. CSought.
Include CAssert and then add assert vertex count is greater than or equal to 3 with the label vertex count must be at least 3. Next, create a local variable of type vk device size called buffer size equal to size of vertices index 0 times the vertex count. So the size of operator returns the number of bytes required per vertex, and then multiply.
Okay, let's vk device size. vk device size, vertex buffer size, size of vertex 0, vertex count. Okay, cool.
Count gives us the total number of bytes required for our vertex buffer to store all the vertices of the model. Next, we're going to call the create buffer function. This is a helper function I wrote that is in the LVE device class. Let's go over this now. So the create
LV device CPP. Okay, which function is he looking at? Create buffer. Control of create buffer. Okay. Yeah.
takes the buffer's size, usage, and
I will change the theme to the island. Island by contrast. No. Island talk. No control. Control F. It's there, but it's not as visible as I hope. And let's go back to the good old theme. For Dracula, everything just looks washed out. No. Yeah, I still like this good old theme.
properties as arguments, and then returns a buffer and its associated memory by initializing the buffer and buffer memory references. This code here should seem somewhat familiar. We have a create info struct where we set some members such as the size and how we plan to use this buffer, and then call a v.
Should we create buffer success? Is not success then fail. Okay, VK memory requirements. Okay, get buffer memory.
create
Let's
function.
just go through his
Then query the
explanation.
buffer's memory requirements so that we can allocate memory of the proper size that also has the required properties that we specified as an argument. Finally, if that was successful, we bind the buffer to the memory we just allocated. Eventually, we will have to rewrite this function once we integrate a memory allocator. Okay, so back in our create vertex buffers function, we have our buffer size, so now call lve device.create.
How do people even make Vulkan like of
buffer? The first argument
like just using Vulkan requires so much information. Making
is
it
buffer size, then
must
next
be
we have
insane.
vk buffer usage, vertex buffer bit.
VIO.
Tells our device that we want to create a buffer that is going to be used to hold vertex input data. Following that, we need visible bit and vk memory property host coherent bit. So make sure to use the bitwise OR operator here, which combines the bit flags together.
Let's just stop typing this out. LV device dot create buffer. I'm guessing there will be one of them. Buffer size. I think it should be the vertex buffer size. Did he rename something? we model CP, vertex buffer memory,
Visible bit
let's see.
memory property tells Vulkan that we want the allocated memory to be accessible.
We made a function just for the buffer size. Okay, I mistyped it here. Awesome. What is it? Salt and no need of const for now. Just follow that. But just make sure nothing weird changed as well. We model CPP, HPP, these are new. Then just the shared asset. Okay, cool.
From our host, aka the CPU. This is necessary for our host to be able to write to the device memory. The host coherent memory property keeps the host and device memory regions consistent with each other. If this property is absent, then we are required to call vkflushed mapped memory ranges in order to propagate changes from host to device memory. Then the final two arguments are the vertex buffer and vertex device memory. Use
Let's
the
go
bitwise
over
or
that explanation
buffer.
again.
The first argument is so back in our create vertex buffers function, we have our buffer size, so now call lve device dot create buffer. The first argument is the buffer size, then next we have vk buffer usage vertex buffer bit. This just tells our device that we want to create a buffer that is going to be used to hold vertex input data. Following that, we need to specify our memory properties with vk memory property host visible bit and vk memory property host coherent bit. So make sure to use the bitwise or operator here, which combines the bit flags together. The host visible bit memory property tells Vulkan that we want the allocated memory to be accessible from our host, aka the CPU. This is necessary for our host to be able to write to the device memory. Want the allocated memory to be accessible from our host, aka the CPU. This is necessary for our host to be able to write to the device memory. The host coherent memory property keeps the host and device memory regions consistent with each other. If this property is absent, then we are required to call vkflushed mapped memory ranges in order to propagate changes from host to device memory. Then the final two arguments are the vertex buffer and vertex buffer memory member variables. Now finally declare a local variable void pointer data. Then call vkmap memory lve device.device vertex buffer memory 0 as the offset, buffer size, then 0 for not providing any vk memory mapped flags, and to data. This
Okay, void store data. Just by making it vk map memory device vertex buffer memory 0 buffer size 0 and data and memcopy and vk unmapped memory
mapped to device memory and sets data to point to the beginning of the mapped
function include c-string.
Then next we need to use the memcopy function. So first include cstring, then call memcopy data vertices.data static cast size t buffer size. And finally call vk unmap memory lve device.device vertex buffer memory.
Okay, so far everything is correct.
So memcopy takes the vertices data and copies it into the host mapped memory region. Now, because we have this host coherent bit, the host memory will automatically be flushed to update the device memory. If this bit is absent, we'd be required to call vkflush mapped memory ranges in order for the changes to propagate. Okay, now the draw function implementation is very simple. Copy and paste the function signature and add the in order for the changes to propagate.
I want to play some background music. No. Each time I pause and play, that will pause and play.
Okay, now the draw function implementation is very simple.
What is even happening? Got lost in
Takes the
between.
vertices data and copies it into the host mapped.
Okay, host CPU copies the vertices to memory, then it gets copied to the buffer memory, guess into like VRAM or something, and then it gets used
memory region.
by the
Now,
GPU.
because we have this host coherent bit, the host memory will automatically be flushed to update the device memory. If this bit is absent, we'd be required to call VK flush mapped memory ranges in order for the changes to propagate. Okay, now the draw function implementation is very simple. Copy and paste the function signature and add the class name scope.
Wide array model bind and okay. Okay, let's see if any of this is correct.
Then inside the body, just call VK command draw, command buffer, vertex count, and then 1 for instance, 0 for first vertex index, and 0
That should be
first instance index, and that's it. The bind function is pretty similar. Copy and paste the function signature and add the class name scope. Make a local variable VK buffer, buffers array, equal to curly braces vertex buffer. And then VK device size offsets array equal to curly braces 0.
okay. Either he got confused in some way. I think it was correct. Let me just change this. Control Shift F6. Buffer. Buffers. Okay.
Then just call VK command bind vertex buffers, command buffer, first binding at 0.
Yeah, if you're doing a bind, it should go with bind. You're doing draw, it should go with draw. I think
Binding count of
he
1, then buffers and
got
offsets.
confused.
So this function will record to our command buffer to bind one vertex buffer starting at binding 0 with an offset of 0 into the buffer. And when we eventually might want to add multiple bindings, we can easily do so by adding additional elements to these arrays. Next, let's implement the getBindingDescriptions function. For its scope, we have LVE model scope, then vertex scope getBindingDescriptions.
Okay. Now the array model should be
Descriptions function. For its scope, we have LVE model.
Yeah, let's see. Only model vertex. There we go. And startup. Okay.
Vector VK vertex input binding description, local variable binding descriptions of size 1. Then binding descriptions index 0 dot binding equals 0.
Binding descriptions 1, binding equals 0, stride equals size of vertex, input rate equals VK vertex input rate.
Then dot stride equals size of vertex, and dot input rate equals VK vertex input rate vertex.
Yeah, pretty good prediction.
Then return the binding description. Alternatively, if you prefer, you can just use a brace construction, but I've done it this way to make the code more readable. So this binding description corresponds to our single vertex buffer. It will occupy the first binding at index 0. The stride advances by size of vertex bytes per vertex. Now finally, for get attributes descriptions, copy the function signature and add your model and vertex scopes. Don't forget to remove the static keyword. So similarly, create a local variable with type vector.
Yeah. Std vector vertex import attribute description. Attribute descriptions.
Of VK vertex input attribute descriptions called attribute descriptions. Attributes index 0 dot binding equals 0. Next dot location equals 0. This corresponds to the location.
Yeah, now it's the same as well. Attribute description. Okay, VK format, offset vertex.
The vertex shader. Next, dot format equals VK format R32 G32 S float. This specifies the data type that we have two components that are each 32-bit signed floats. Finally, dot offset equals 0 and return attribute description.
32, 32. Okay.
Next, we need to provide our pipeline with these descriptions so it
offset equals 0. Return attribute. Save.
read our vertex buffer data. First, we need to include our model class. Now, currently in
our pipeline,
line function, our vertex input info struct was pretty much empty. Start by adding two local variables. Auto binding actually knows how to read our vertex buffer data. First, we need to include our model class. Now currently in our create graphics pipeline function, our vertex input info struct was pretty much empty. Start by adding
let's see.
two local variables, struct our vertex buffer data.
Let's doing it on the pipeline.
First, we need to include our model class.
Dash include model HPPP.
Now currently in our create graphics pipeline function, our vertex input info struct was pretty much empty.
Create graphics pipeline.
Currently in our create graphics, first we need to include our model knows how to read our
I hated this in the CPP version. V Control S.
First, we need to include our model class. Now currently in our create graphics pipeline function, our
This stuff is so dull. But to progress, you have to learn this stuff.
vertex input info struct was pretty much empty. Start by adding two local variables. Auto.
Okay, where is this? Make it pipeline import state character. Auto
is equal to LVE model vertex get binding descriptions.
Auto binding description. just content or content. Hmm. Okay, still goes to the next line. Whatever.
And auto attribute descriptions is equal to LVE model vertex get attribute descriptions. Then update the attribute description count to equal static cast uint32 type attributes.size.
Vertex description. Startup cost uint later t packet
Description count to equal to static cast uint32 type binding descriptions.size.
Hmm. Say attribute and then binder. Attribute startup cost uint then 32 uint 32t binding descriptions dot size dot size semicolon. Is the show context options. Possible erroneous expression without side effects. Okay.
Then set p vertex attribute descriptions to attributes descriptions.data and p vertex
Yeah, this should be a dot. Save. Yeah.
descriptions to binding descriptions.data. Now all that's left to do is create an instance of our model and draw it. So open your first header, include LVE model, and p vertex binding descriptions.
Let's see. Attribute descriptions dot data. And this will be binding descriptions dot data.
Data. Now all that's left to do is create an instance of our model and draw it. So open your first header, include, and then create a LVE model.
LVE model.
Unique pointer LVE model. Then add a private load models function.
Let's see, adding it. Local on std unique pointer LVE model. LVE model.
Now in the first app implementation file, implement the function void first app load models.
Windows start create draw frame into this. Or first tab, load.
Inside its body, create a vector of type LVE model vertex, and we will use this to initialize the vertex data positions. So I'm going to use the same position
Or just finish models. STD, vector, IV, model, vertex, vertices.
we had before of 0, negative 0.5, 0.5, 0.5,
0. Only brackets, only brackets 0.0 f minus 0.5 f. 0.5 f. Let's copy this, comma, paste, comma, paste. Okay. Oh, what? Okay, it just has double brackets. Control V, Control V. What got deleted? Okay, it's at least
the outermost
consistent
initializes the
now.
vector, then we initialize each model vertex, and
Now get
most braces initialize the GLM vec2 position member. Next, initialize the model with LVE model equals std make unique LVE model with LV
to enter the correct values. And minus 0.5 and 0.5.
as the first argument
Mm,
and vertices as the second. Then in your first app constructor,
Okay, already model. And for STD, make unique.
load models function as the first line.
What happened? Can load models. Cannot resolve this.
Then equals S vertex, and then the innermost braces initialize
Okay, a semicolon is a
the GLM vec2 position member.
have to keep stretching my leg, otherwise it will fall asleep.
Next, initialize the model with LVE model equals std make unique
Yesterday, make
LVE
a
model with LVE device as the first argument and vertices as the second. Then in your first app constructor, call the load models function as the first.
can load models. Exactly the issue. Also, constructor does not initialize these fields.
Then in the create command buffers function, remove the command draw function call and add LVE model arrow bind command buffers at index I and LVE model arrow draw command buffers at index I.
Let's just add all these things first. Create command buffer. Where was this? Here. Okay, let's see. LV model. Bind command buffers. And we need a draw. Did not create this variable somewhere.
And that's it. Our command buffer in each render pass will bind our graphics pipeline, then bind our model which contains
Fetch. This one is still there.
vertex data.
Why did we create the LV model there?
Then add a private load models function. Now in the first app,
Yeah, this was an HPPP. Private word load models. No, first step CPP. I'm missing
documentation
something.
file,
This LV. Okay, fixed. Does not initialize this field.
implement the function vertex contained by the model. Now build and run, and okay, I've done something wrong. It's an easy fix. I swapped the names of the bind and draw functions. Also
Yeah.
make sure that your vertex shader has been recompiled if you haven't set it to automatically do so. If I fix that and now build and run, our familiar triangle appears. But what's different this time is that the vertex positions are no longer hard-coded into the vertex shader. Finally,
now let's build and see. Okay, so drawing it correctly. Yes. After this, I'll look
completely optional
into
exercise. Now that we can provide
having
any
it
position data we
automatically
want,
recompile the
see if we can
shadows.
create something like the Sierpinski triangle that's displayed in the tutorial's thumbnail. You will probably want to create a recursive function that generates a vector list of vertices. Every 3 vertices forms the next triangle. Then initialize your model with that vertex list. I've included a link to my solution in the video's description. And that's it for today.
Okay, what did you do? Sierpinski triangle solution. Vertices push up, push. What is all of this? Okay, for now, let's save all the current changes. This was tutorial 6. Get. What is this? Hold request. Okay. This can go here, and I'll hide it, honestly. I don't need it right now. Save everything, commit and push. It's pushing. Yeah, done. Now, if you want, we can do as that code. Yeah. I just put it in the CPP file. And I just okay, and load models. I have it. Array vertices. And you have to add some over here. Slow, avoid, save, or even space. Let's copy the spelling. And let's see. First, save. No, this doesn't look right. Yeah. Where is the error? VM model vertices. Problems. Function has 0 parameters but is called with 5 arguments. If else, let me just copy this directly. Yes, second scale. I will show it as like not. I do have to add all of these. Models of frame. Yeah, copy this whole thing. And this. And is this. Right when the function started. No, nothing important. Let's try running it and see. Did OBS crash? Hmm. How long has it been a crash? Okay, shall close and shut down. Or just restart OBS.